President Fink, ladies and gentlemen. Those of you who listened attentively to this introduction observed that I am associated with RCA, and some of you know that RCA is a fairly large company. Not as big as a local company, but we were started by them, so we have to grow a little. But we are a fairly large company and operate a number of subsidiary companies. One of these subsidiary companies goes under the heading of National Broadcasting Company. You may recall they operate an entertainment service. And one of the functions of this entertainment service is to precede each program with a commercial. Now that policy, of course, affects me, and I'm going to give you a short commercial on our laboratories through the medium of 4 slides, actually. This is a view that you would get of the laboratories in Princeton, halfway between New York and Philadelphia. If you arrive by helicopter, not many people come that way, but it's still a view you would get. And you'll observe that we are surrounded by a large lawn, about 180 acres. This we find a very useful adjunct because when our research engineers get to be a little sluggish, we give them a lawnmower and tell them to cut an acre or 2, and they're right back on the job again. Moving into the laboratory, you see the usual chemist puttering around. I'm a little suspicious that he mixed together some solutions just for the benefit of the photographer, but he also does useful work on other occasions. And then the next slide shows the usual puzzled engineer looking over a circuit, wondering why it doesn't work. Of course, he always gets it to work, and he might even get a patent out of it. And then in the next slide, you see the organized approach of the research engineer to his problem. We've been engaged in electronic research for quite a long time, and this electronic business I find falls into 2 phases. The first I'll call the older electronics and the newer electronics, to which I'll refer a little later. But to bring you up to date on the old electronics, I guess we'll call for the next slide, which sets this forth. In the past, we have learned how to get electrons out from their parent atom and out into free space or out into a vacuum or into gaseous medium, and we do this by boiling them out in the old thermionic tube. And we get some electrons out by bombarding or blasting surfaces, photosensitive surfaces, and we have the photoelectric effect. And we get others by banging them out onto special surfaces where one electron will kick out 3 or 4 or 6 others, and we have a gain in amplifications. And once in a while we even blast them out by radioactive means. But in each instance we get the electrons out from the parents out into free space, and we are then able to control these electrons to make us to do all of these fabulous things which electronics has brought to us. More recently, we've been working on electrons within solid materials, and I'd like to refer to a couple of illustrations of that. The next slide refers to one which is fairly important in that it is an outgrowth in some respects of the many years of research that have gone into phosphors. We have been engaged in phosphor research for 25 or more years. This was important for television because phosphors are those materials which translate finally the electrical impulses and currents and signal into something you can see. I didn't know it at the time, but this phosphor research was a phase of solid-state physics because the structure of the crystals and the presence of the electrons and various energy levels makes them work. We didn't know it, but this is solid-state physics. More recently, work has been done on the phenomenon of electroluminescence, where you put an electric field across certain materials, cadmium sulfide in this instance, and if you put an electric field across those materials, every once in a while the field will kick an electron away from its home base upstairs into some attic or some balcony, and at a later time this electron will fall back into a hole which it or another electron vacated. In the process of falling back, it releases the energy which originally kicked it upstairs, and that energy appears in the form of a photon. Cadmium sulfide at least produces that effect. The photon is a little bundle of light, and the energy that's released is exactly 2.4 electron volts. Now I can remember this quite easily because it's printed so plainly right here. Now you may not know exactly how much 2.4 electron volts is, and so I ought to tell you that 2.4 electron volts, or an electron volt rather, is about 1/trillionth of an erg. That's all right if you know how much an erg is. But unless you have had a course in elementary physics in the last 2 or 3 weeks, you've forgotten about this. And I'll have to tell you what an erg is. Well, this is easy to define also, because an erg is about the amount of energy which a housefly expends in doing a morning push-up. An electron volt is 1/1,000,000th of this. So I will illustrate electroluminescence in a moment, but before I do, I'd like to refer to another slide which has something to do with modern solid-state physics, and that is the photoelectric effect. In certain crystalline materials where these atoms are all bound together with a crystal lattice, a catastrophe occurs once in a while when a photon comes in and breaks one of those bonds. And in breaking the bond, it releases an electron which is kicked upstairs into a conduction level, and then where it had been sitting, it leaves a hole, and since there's no electron there, there's a net positive charge. And if an electric field is applied, the positive charge moves to the negative electrode, and the electron moves to the positive electrode, and there's a current flows, which is a function, among other things, of the intensity of the light that falls upon here. Now, this is no different than the old photoelectric effect of phototubes and even selenium, but we are able to enhance this effect because we've learned more about materials. Now, I can illustrate this over here with 2 panels. This first panel is an electroluminescent panel and is so arranged that if I place an electric field across it, it will become luminous. So as I apply this field, you will see now a luminous panel. You may not like the green light, but we've learned how to make these panels of other materials, so we get other colors also. This is, we think, one of the next phases of industrial illumination. As a matter of fact, the fluorescent lamp, which is so common to all of us now, actually was an outgrowth of the work that we did in our laboratories on phosphors. The next phase will probably be industrial illumination, where we have luminous panels. Now we have another panel here which is a photoconductor, and in the dark the resistance of this is fairly high. So if I connect the voltage across the two in series, in the dark there will be so much resistance that no current will flow. So as I apply the voltage there, nothing is happening. But if I shine a light on the photoconductor, it will reduce the resistance and current will flow. And the amount of current that flows, and hence the amount of light in the electroluminescent panel, is a function of the amount of light that falls upon the photoconductor. Now, some of you will say this is certainly no different than you can do with a phototube, and I completely agree with you, except that here we're not dealing with electrons out in a vacuum in free space. We are dealing with electrons that we are controlling within solid materials. Now, you may wonder where we get all of these problems in which we can work, and I'll say they come from a variety of sources. We think we have fairly intelligent research engineers, and they see these interesting phenomena, and they begin working on them and make new and important discoveries. Once in a while their bosses have ideas too and make suggestions, and we're apt to follow those out. And many of you know the story now that occurred really a number of years ago of the big party we had in Princeton for our big boss. His name is David Sarnoff. He's chairman of the board and has been, as far as I can remember, as long back as I can remember at least, and he probably will continue as long as most of us can remember. But nevertheless, we had this celebration, and the General Sarnoff had completed 45 years of association with RCA and predecessor companies. RCA isn't that old, but he worked for Marconi, and Marconi was a part of the forming of RCA back in 1919, and so he had uninterrupted service with RCA and predecessor companies. So we had this great big birthday party in Princeton, and there were many speeches that were made, and many complimentary remarks were passed around, and then finally the general got up and made a speech, and he was very expansive, and he said, "This is really a wonderful occasion. You scientists have given us so many, many wonderful things. The research that you have done has led to numerous electronic products that we have been able to manufacture. A few of those we made a profit on them, and this has been really a great evening, a wonderful birthday party." But he says, it's nice once in a while to drop some hints for presents for your birthday, and if all goes well, 5 years hence I will complete 50 years, and I would just like to ask for 3 birthday presents. And so we all began to sit up real straight and wonder what he was going to ask for, and we didn't have long to wait. The first thing he said he would like to have is a system of recording color television signals on magnetic tape. Well, back in those days, we were still trying to get 15,000 cycles in magnetic tape, and I looked around and there were quite a few amazed looks in people's faces. However, we got busy at this the next day, and actually before the year was over, we had demonstrated a preliminary system which, and as many of you know, this is now widely used commercially. Well, by this time we were wondering what else he could ask for, and sure enough it came very quickly. He would like to have, said he, a system of direct light amplification. And I looked around, there were quite a few Adam's apples popping up and down, among those particularly who thought they would have to work on this, and they weren't disappointed. They did. Well, he said television, of course, is a light amplifying system. You have a camera which looks at a dim picture and you come out with a very bright picture in a picture tube, but this goes through all kinds of electronics. What we want is to have something where a little dim light will somehow be converted into a very bright light, just like a little bit of voltage on the grid of a tube can control a large plate current, which in turn can be translated into a large voltage. So a little voltage produces a big voltage in a radio tube. Well, we didn't have much idea how to do that, but in a little while I'll show you how we accomplished that. And by this time we were really sitting on the edges of our chairs wondering what in the world he could ask for next. And here it came. The next thing, said he, I would like to have is a system of electronic air conditioning. In that instance, several people fell off their chairs from amazement. And we just wondered how in the world this could ever be accomplished. Well, a little later I hope to show how this will be done too. Back in the days when I was doing research, we were working on radio frequency heating, and my boss and I used to jokingly say it sure would be nice to have an electronic refrigerator, but of course we knew this couldn't be done, and so we just had a big laugh about it. But when the general said he wanted it, we didn't chuckle quite so loudly. Well, now in this matter of getting a light amplifier, we knew about these two effects, and we thought this would be a way to accomplish it using these two principles. And so we made a panel. This is a very crude way of illustrating how this was done. First of all, we have learned how to lay down a layer of, or a coating on a glass so that it is transparent, and then we laid down a layer of electroluminescent material, and a little bit later we laid down a photoconductive layer, and finally another electrode. But in principle we have a photoconductor here, and when light shines upon it, the resistance goes down, and current will pass from here through the other side, through the electroluminescent layer, and a spot of light appears at that point. And the interesting thing is a dim light on this side will produce a very much brighter light on the other side. In order to translate this into action, we put it in a panel, and it's enclosed in this box here because the panel is somewhat sensitive to light, and until I'm ready to turn it on, I don't want to destroy its sensitivity. And for subject matter, I have merely a slide here which I will put in or shine on here, and you can see this. Now I'll open the box, and we will shine the subject matter on the photoconductive material. And then we will not actually use it this brightly. We'll turn it down to about this level, which you don't see nearly as well. And then we'll swing it around to the other side and see what we have, and we discover that we have nothing because I haven't turned on the voltage yet. So as I apply the voltage here, you see the picture appearing. As you look at this picture and compare it with the picture on the other side, you will see indeed there is an enhancement. We have a gain in this unit, and this is the very first one that was built, a gain of about 40 times. We have made other amplifiers which have a gain as high as 1,000 times, and we couldn't run it with even this much light in it. The important thing is that it works from a very, very low level to a useful level, and one of the places in which this has come to be the most useful so far is as an X-ray intensifier, because this photoconductive surface here can be excited by X-rays, and we can take a very, very dim X-ray picture that could not be seen by an ordinary fluoroscope, and we can brighten it up so that we can take these pictures, see them or take pictures of them, and this also has a storage characteristic so that we can take a very intense X-ray picture of a very short duration and store the picture long enough to photograph it. what started out as a research project now is reaching a point where it becomes effective. Well, on this problem of getting electronic refrigerator, that really had us licked for a little while. Hardly ever think of occasion when a current would pass through the wire and the wire would get cold. Usually it warmed up. But then we thought a little bit more, and we remembered an experiment that a Frenchman did back in 1834. Mr. Peltier passed a current through a junction of two dissimilar metals, bismuth and antimony. He found under certain conditions that this would cool, and he got a temperature depression as much as 16 degrees Fahrenheit. Now that was an interesting experiment in physics, but of no real practical value. But as we began to work on this, we thought we ought to take another look at the Peltier effect and see why it worked. And we made some discoveries that I don't think Mr. Peltier suspected, and the reason that the bismuth and antimony worked was partly because it was bismuth and antimony, but they were not perfectly pure. There were slight impurities, and one of these happened to be a P-type material. It was a material in which there was a slight absence of electrons, or holes were present, and the other was an N-type material in which there was a slight excess of electrons. And it turned out it was the P and N-type characteristic that really made the cooling effect take place. These P and N, the holes and electrons were the carriers of heat. Well, we'd learned a lot about making P and N-type materials in the last few years, and so we embarked upon a program of research in which we just made many, many hundreds of alloys to see if we get a good thermoelectric effect. Now, since we were going to pass a fairly heavy current through this, so something in the order of 25 or 30 amperes, these alloys had to be a good electrical conductor. In nature, most good electrical conductors go together with a good heat conductor. Well, after pumping this heat out laboriously by electronic means, and I could take the time to tell you how this works, but in the words of textbook writers, it can be shown that this does happen. And I could use a lot of big words about Fermi levels and preferred bands and forbidden levels and so on, and I know the words, but I won't foist them upon you. We could show how this actually is an electron pump, and the electrons moving up here actually carry little infinitesimal bits of heat along with them and deposit them up in the terminal point here, and this heat is carried away in this instance by a small flow of water. In this instance, the water flow is a little bit bigger than expected. And in the holes, which is a little harder to explain, the holes carry the heat up here and deliver it to this terminal point. Well, we had to pass about 30 amps through here, and that meant it had to be a good electrical conductor, a poor heat conductor. Also, it had to be a good thermoelectric material, and when we had all of this done, we had materials to which nothing would solder. And so we had to invent a little solder to tie the whole thing together, and we finally got the thing finished, and we made a junction in which this part would be depressed 20, 30, 40, 50, and once in a while 60 and 70 degrees centigrade below ambient temperature. Now we were reaching the point where it would be a useful device. And so we actually built a little refrigerator. A number of these were used to freeze ice, and this is what I have in here and to work. But I have a little unit here, and I'm circulating the water through the warm junctions, and here, surrounded by insulation, is the little cold junction. I'll put a little water in there, and then after a while we'll come back and hope for the best. Now, there isn't really very much power going into here. I talked about 30 amperes, but the voltage across this is only about 1/10 of a volt, a little bit more, so we're putting around 3 or 4 watts into this. Well, the first refrigerator we built required a flow of water to carry the heat away. This was a good laboratory experiment, but of no real practical value, and then we continued and later on learned how to make the junctions with radiators. We had the P and the N-type junctions here and the heavy current leads, and this is the cold plate, and this radiates out into the atmosphere, and with a large number of these we were able to make a refrigerator, which is shown in the next slide. Now, this looks like any other refrigerator because that's the only way we knew how to make it. It has a cooling compartment of about 4 cubic feet, and it makes a tray of ice cubes. It's not as efficient as a mechanical refrigerator, but we haven't been working as long on it, and actually it's perhaps 25 or 30% as efficient. But there's nothing to wear out, there's no noise, there's no gas to leak, and it's kind of tough on those who make the living servicing refrigerators, but I don't think you have to change jobs until, at least not until next week or maybe even the week after, because this is not quite ready for production, and don't hold your breath waiting for it to come, because there's a great deal of important fundamental research that still has to go on. We've done the easy things. We're a little bit more than halfway there, we believe, but we have made this sort of a unit, and it's been running for, well, a good many months, perhaps several years, a couple of years at least. However, General Sarnoff was interested in a refrigerator, but his request was for an air-conditioned room. And in order to accomplish that, we used the same principle, built an element in a slightly different way. We again had the P and the N type alloys arranged in such a way that these are now the cold plates. The insulation of the wall goes through here. This is out of doors, radiating into the out of doors, and so we put many dozens of these in a wall for a cold plate, and this is cooled electronically. And no noise is heard because you just don't hear these electrons pumping the heat out. They do it very quietly. And I guess you could hardly say they're a moving part. Of course, it depends on how you define the part. Well, we actually built a room using a number of these, and that's shown on the next slide. And if you can get by the young lady in the doorway there, you will see a panel on the wall, and there's another one here on this side, and this room can be cooled real nicely. 4 small people can play a cozy game of bridge in there. And several times I was in there, it was so cold we had to open the door. It was down to 56. Of course, you can always shut it off, but why shut it off? Just let it, we're life testing it and see how long it would run. One of the interesting aspects about this is, of course, that we do get a circulation of air without any fans because the panels cool off, the air sinks down and circulates around by convection, and we don't have any cold blasts, and of course there's no noise. And one of the other aspects about the Peltier effect is that if you reverse the current, the junction will warm up, and so you can think in terms of having 2 buttons here. The first button will be marked cold, and that'll cool the panels, and you have an air cooling system, and then the other button will be marked warm. In the winter you can reverse the current, and these now become warming panels, and you have a means of warming your room or cooling the room depending upon the requirements. Well, now while I've been talking here, this thing has been running, and I don't know if it's quite had a chance to freeze, but I'm going to try to use this reversing effect, and I'll reverse the current and thaw out the little bit of ice which I hope I have made here. And I have here a small electronic popsicle. Now this is just ordinary ice. It's no different from the kind of ice you can get here in Pittsville without any moving parts in January just by setting a dish outside. But this is an electronic popsicle. While in research we aren't too concerned about economics, I did get a little interest in this. I did a little calculating and figuring the cost of the equipment and prorating some of the research into this. I find these popsicles are now could now be sold for a little bit less than $8 a piece. They will get cheaper as time goes on. This illustrates, of course, how research engineers like to do easy things the hard way. Will you have an ice cube, Mr. Fink?
Thank you very much.
Now, in another area of this solid-state electronics, we have been working on electronic photography. Now, many of you are interested in photography, and you know, of course, that photographic paper is very sensitive to light, and you don't like to expose it to a bright light such as this because that spoils the paper forever and for keeps. However, with this electronic photographic system, we don't have to take those precautions, and we find that this paper is not affected by ordinary light or radiation, as far as we can tell, even by age. Now, as you might suspect, this has a coating on it. In general, I don't disclose what this coating is, but I've just had such a wonderful time. You've all been so good to me. I feel very generous. And I'm going to tell you what this coating is. It's house paint. Well, it isn't quite house paint. It's zinc oxide, which is a constituent of house paint. It's rather carefully purified. But this zinc oxide is one of these materials which in the dark is an insulator. And when light falls upon it, the charge will leak away. So if I want to use this as a photographic device, I can charge it, and I'll have to turn on my safe light. This is just an ordinary bug lamp. This has been adjusted so that it's insensitive to the yellow. And then to sensitize it, I will lay down on here a layer of electrons with a charging device. I have a little power supply, and to puts about 5,000 volts on a thin wire, and if you want to look at it one way, the electrons are sucked out by brute force and they land on this paper like hoarfrost and rooftop in January, or like frosting on a cake, depending which analogy you like the best. And now if I wanted to make a contact print of any subject matter, which I happen to have by strange coincidence with me, I will shine a light on here for a matter of a second or so, and where the light falls upon the paper, the charge will be dispelled, and where the light was shielded by the opaque subject matter, there is left on here a latent charge image which your eye cannot see. To develop this, we have to have a developing device, and I find a dirty old shaving brush very helpful. Actually, this is a magnet with some iron filings, but the important part is in the iron filings there's a black plastic powder which becomes positively charged by rubbing together, or the fancy word is by the triboelectric effect. If you dust this on here, the powder sticks to the charge pattern, and I make my picture just like that. Now in this form, it is not yet permanent. After a little while the charge will leak away, and this can be rubbed off, but this could be put into an oven at 140 degrees for 4 or 5 seconds. The black plastic powder would fuse onto the paper, and you have a permanent print. Now we can also use the techniques of projection on here and sensitizing another segment of the paper. I have a slide here which I will use as subject matter, and we'll bring this forward into focus, expose once more for a second or so, and we can make a charcoal picture faster than even the best of you can do it. Now one of the more interesting phases about this is that if this should happen to be a little too dark, why that doesn't bother. You just shine a little more light on it and tone it down until you reach the value that suits you. Now, if for some reason you wanted to erase part of this picture, I'm not sure why you'd want to do this, but just you might want to for some, this is a technical reason, as we're engineers, you don't always let your emotions take hold. We find that this is a useful brush because not only does it make the picture, but it also rubs it off. See, what's happening is that as the light shines on here, charge is dispelled, and the black powder now finds greater affinity for the brush than it does for the paper. And now if we wanted to add any further information on here, we could charge up again. We can make another exposure. And now to develop it, I'm going to use a little different scheme. I have some electronic salt here. We'll sprinkle a little salt on. And you see, we can accomplish it that way. Now, we certainly don't want her to lose her fine hairdo, and the ladies in the audience know, of course, that you can get some stuff called a spray set, which is good for keeping your hair in place. And so we can set this picture again by putting on a little clear lacquer, and with a little care I could perhaps even make a better print, but we're only illustrating principles. See, in research we only illustrate principles, we let engineering make them practical. Now the nice thing about this electroflex process is that you can put it down on any sort of a surface, large or small, wood, paper, glass, metal, anything at all. It's been used for template work. We've done some work on printed circuitry. Many of you know, of course, that in a printed circuit you have a clad piece of bakelite. You put photographic emulsion on there, you expose the picture of the circuit, you develop it photographically, and then finally you etch it, and you have your finished circuit. Now, with electroflex, you can take your copper-clad bakelite, put the zinc oxide on there at once, lay on a charge, and then develop it as I showed you a few minutes ago. And the black powder can be set in literally a few seconds with an infrared lamp, and you're ready for etching right away, and you can make a printed circuit. This is not exactly a printed circuit, this is an etching a friend of mine made out in Minneapolis a few weeks ago when I was out there. But it illustrates how this can be done. And sensitive-wise, just a reference point, it takes about 30 watts of fluorescent lamps at 2 to 3 inches, 2.5 minutes to expose a picture on photographic methods. Here you take two 4-watt lamps, at 30 inches in a half a second to make the exposure. This Electroflex paper is about 100,000 times as sensitive as Ozolid blueprint paper, for example, and we can make multicolored blueprints. These are just a few of a number of applications that have been worked on and are being developed by our own company and by other companies. Well, as a good many of you know, one of the other phases of activity of RCA, in which RCA has long been engaged, is that of television. We've really been in television a long, long time. The name of Dr. Zworykin, of course, is very intimately linked with television, and Dr. Zworykin had this concept of electronic television many, many years ago and built a camera tube to pick up a television picture. And this first camera tube which he made before the end of 1923. Most people hadn't even heard about radio in those days, and here was Zworykin making a television camera tube. Now that wasn't a very good tube. It required a 1,000-watt lamp about 4 inches from your face to get any kind of a picture at all. Over the years we conducted research, the most important of which, well, image orthicon tube is the standard tube of television today. This is a very wonderful electronic device. This is a very important tube and a very sensitive tube, and under special conditions this tube has picked up a picture by bright moonlight, and that's 1/1,000,000th the amount of light that Dr. Zworykin's first tube required. Indeed, with some special a few changes within the tube, we've made some special tubes which will pick up a picture by bright starlight. Now those weren't broadcast quality pictures, but the subject matter frequently was quite interesting. Well, as important and as impressive as the performance of this tube is, there are many places we felt that television should be used, and we just didn't have room to put a big tube like this or the expensive or elaborate equipment. And we did some work quite a few years ago on making a simplified tube, and this is the one that developed the Vidicon, which again is a solid-state device because the photosensitive surface is a semiconductor. It changes its resistance as light falls upon it. It doesn't emit electrons as this one does. And with a tube like this, it was possible to build a camera about the size of a standard amateur 16mm motion picture camera, and our own company and a number of others have made a number of devices where we can help industry see where it can't look. We can put television in hazardous or inaccessible locations, and this has opened up a whole new field of industrial television. Well, we thought if a small tube was good, maybe a smaller tube would be even better, and so we continued our work, and we have come up. This has about the same performance characteristic as these other tubes have. And while one group in our laboratories is working with this, other groups in our laboratories are working with other solid-state devices, the transistor, which is so well known now. And it occurred to somebody it would be nice to see if we couldn't build a camera with a few transistors in one of these tubes. And so we struggled around that for a few days, and we actually built a tube and built such a camera, and here it is. Now this is actually a little bit more than a camera. We feed power in here through this thin wire, about 5 watts at 60 cycles. And then there's a little transformation takes place in the camera, and a tiny fraction of a second later, I don't know just how much later, it's almost infinitesimally later, we come out of this same wire, not with 60 cycles, but with about 60 million cycles in a picture. Or more specifically, a full television signal on channel 2 or 3. And this feeds over to the antenna binding posts of a standard receiver. And so if we turn on this receiver over here, we can pick up a signal that is being picked up by that camera and transmitted by this fine cable over to this point and applied to the antenna binding post. Well, there we're transmitting this over from here to there, and a picture even under illumination conditions that would hardly be ideal for photography. And while this again isn't broadcast quality, if you knew the guy, you would certainly recognize him from that picture. Now there is a completely self-contained system, and just to give you a little idea of how it looks inside, we can swing this open here, and we get at it this way. 19 transistors and 1 vacuum tube, and here's the transmitting station down at this end. This tunes from channel 2 or 3, because in any community you'll either have channel 2 or channel 3. In Princeton we can get them both, so we have a little trouble there. This gave us courage to take a look at a project in which we had worked a number of years ago when we came out with the 1-inch Vidicon back about 1950, I guess it was. Somebody looked at the calendar and remembered there would be some political conventions a year or two hence, and they thought it'd be nice to make a portable television station using a tube like this and a backpack transmitter. And so we built such a one. It finally weighed about 65 pounds, and it took a real strong, recently mustered out GI to carry this for more than 15 or 20 minutes. We didn't have a name for it. We thought about a number of things. In radio you had the walkie-talkie, and this might be called the walkie-talkie-lookie, and that didn't go so well, and this matter of a name hadn't been settled. Well, one Monday morning, one of the younger engineers working in this group, it was his turn to carry this. We just had to pass the honors around. And this fellow was a man of slight build, and it seems he'd been out in quite a weekend. The weekend wasn't quite over as far as he was concerned, but it was his turn. And so they put this thing on his back, and he just wasn't up to it. He sagged down on his hands and knees and was crawling around on the floor. And just then an engineer came through the door, and he says, "Oh, I see you're using the creepy peepee," and there we got a name. With the mini Vidicon and transistors, we thought we ought to take another look at this creepy peepee business, and we rebuilt it, and the next slide shows what happened. We now have a backpack transmitter that weighs 15 pounds and is about 10 or 11 inches square by about 3 inches thick, and the camera is up here, and we have a viewfinder which we can separate from the camera. This has one vacuum tube in it, the Vidicon, the mini Vidicon, and this has one vacuum tube in it, a 1-inch kinescope, works exactly the same as your 21-inch kinescope at home, and then one 2,000 megacycle vacuum tube for transmitter. So we transmit at 2,000 megacycles, and the rest is done with transistors, about 75 or so. One of the more interesting engineering phases of this is that this has a sync generator in it, which must be all of 2 inches high and 2 inches deep and about 7 or 8 inches long. And when this thing goes on the air, that little sync generator took a hold and controlled every television station in the country that was broadcasting its signal, and every receiver, of course, that was tuned to that particular station. So we had this one little crystal-controlled oscillator, or sync generator, right in here running the whole country. The matter, of course, of building this and getting it to work was a bit of a problem, and one of the engineers who worked on it, George Gray, was to take it out to the conventions a couple years ago now. George Gray is quite an avid flyer, and he has a very good plane of his own, and one day he was walking down the hall with this thing under his arm, and one of the vice presidents says, "Where are you going, George?" "Well," he says, "I'm going to Chicago. We got a convention out there next week, and I got my plane warming up out here. I'm taking off in a few minutes." And he says, "Oh, no, you don't." "What's the matter?" "I said, I'm supposed to go out there." He says, "You can go out and fly your plane and break your neck if you want to, but you can't take this with you. This is the only piece of equipment that exists. You cannot take it with you." And so we had to get one of our truck drivers, wrap it in a big box, and took it out carefully in the train. Well, we got it out there all right, but George's problems weren't over. He could take all the pictures he wanted, as long as they weren't in the air. But as soon as he went in the air, he had to hand the camera over to somebody else. It seems George didn't have a certain card of some sort in his pocket. I don't know what it said in that card, but he didn't have one anyway. And then one day he was fixing something, and he's on the floor, The guy came streaming in the side door, and he says, "Hey," he says, "you can't fix this." And George says, "Yes, I think I can." "Oh," he says, "I don't mean it that way, but," he says, "I don't think you belong to the Amalgamated Association of Television Camera Fixers." So George wheels out about 6 feet of blueprint and says, "You fix it." The guy looks at him for a while. He says, "Well, you've gone this far, you might as well finish the job." Well, you see, our problems aren't all research problems. You have to deal with people. Television is sort of a communication medium, and we've been in the communication business for a long time, and another group began to think about some of the problems of communication. Dr. Olson in acoustics prepared a chart, and in a somewhat simplified form, I'd like to show you that in the next slide. If you're talking about communication, the problem is to get from a sender to a receiver. And you can do that a number of ways. A sender, for example, can talk to the receiver, direct contact, and if they're too far apart, they invented smoke signals, and then Mr. Morse invented the telegraph, Mr. Bell invented the telephone. All of these are means for someone to get his message over to someone else, from a sending position to a receiving position. Now, most of these are all essentially point to point, one person to one person. And then we have a number of mass communication media, like the phonograph, the movies, and the radio and television, where an individual or a small group of individuals as senders get their message across to many hundreds, thousands, or millions of individuals as receivers. Now, this was all right in the earlier days when we always sent much more than necessary to be sure there would be enough. As our channels got more and more crowded, we had to take another look at this, and we began to think in terms of analyzing what the sender was about to send and putting it in some sort of a simplified coded form and then resynthesizing it at the receiving end. And I'm going to spend a little time talking about the synthesis of music, but we and others have done work on analyzing sounds and coding them and synthesizing speech. We did some work on taking oral sounds and analyzing them and having it operate a typewriter directly. We've built a phonetic typewriter, an experimental one. As part of this study, we found that there were about 40 different sounds that were necessary. And in a simplified form, these could be collected together in about 1,000 different ways, depending on how complex or how simple you wanted to make it. Well, these 1,000 different ways would give us intelligible speech, and this would come out phonetically. That meant the spelling wasn't always right. In fact, it was only about 50% right, but that's about as good as most engineers spell anyway, so we were right up there already. And then, of course, we could take those signals of the typer and have it synthesized into speech again. We haven't pursued that too far. But I'd like to talk a little about this whole matter of music, which is sort of an interesting topic. We have had music with us a long time. The ancients had some sort of a method of recording musical notes and had some system of music. Sometimes their scales are very primitive. Many of them are different from our scales. And if we listen to Oriental music, it sounds strange to us because they have a different scale. The Chinese have 22 steps in an octave in a full scale, and some of these are quarter steps, and the Arabs have 16 steps, and some of them are unequal, and that sounds strange. The old Gaelic people had only 5 steps. Incidentally, you can play Auld Lang Syne with just playing the black notes in a piano. The bagpipe sounds strange to us because they are tuned to another scale and with the ones with which we are familiar. But we've all had some sort of a system of musical interpretation. No great amount of analytical work has been done on this in the earlier ages. Pythagoras did a little study. He found the relationship that existed between the notes of an octave, the 2-to-1 frequency relationships, and with vibrating strings and dividers, he had 3-to-2 and 4-to-3 and so on. He found there were certain combinations there. But then for about 2,500 years, the whole business lay dormant until some character by the name of Fourier discovered that a series of simple sine waves could be added together to give a complex wave shape, or take a complex wave and break it down into simple sine waves of various harmonic relationships and various amplitudes. Helmholtz, back in about 1860, Fourier did this in 1822, and then Helmholtz about 1867, did his famous experiment with resonators, where he had these spheres, resonant cavities, which would respond to only one particular frequency, and he made a large number of them. Some of them had a certain frequency response, and some would have 2 times and 3 times and 4 times and so on. And then he sounded a note in the clarinet, and he had a fellow running around listening to these. And he found that the fundamental would sound in the clarinet, the one that had 3 times the frequency response would sound, one the 5 times. And he found that certain instruments had odd harmonics, and certain instruments had all harmonics, and some instruments had only the even harmonics present. And he indeed tried to synthesize a few tones with tuning forks. It was a little awkward to run around, keep hammering these tuning forks to build these tones up. So he was a little at a disadvantage. Now, actually, in spite of the very complex nature of music, which gives us pleasing, intelligible effects, the musical note is quite simple, and there are only 6 elements. And Dr. Olson, who was director of acoustic research in Princeton, and his colleagues thought it might be nice to examine carefully what the elements of musical note were. And just like the chemist, who has at his disposal some 90 or 100 elements, the chemist has combined these into a fantastic number of materials synthetically. Many of these synthetic materials have properties far better and beyond those available in nature. So Dr. Olson thought if we have these musical elements at our disposal, we can combine those in ways that normally are not combined through natural sound-producing means. Now, these 6 characteristics are set forth in the next slide, and they can put them up there just for a reference point. And I'll find that we have the first one that we can look at is pitch. We can hear from cycles through to 15,000 cycles. Now, some of you know exactly how much 30 cycles sounds like. Some of you may not be quite so sure about that, and so I will illustrate this in a moment. Run this up. This is 300, and this is 3,000. Well, I'll give you one or two more just as a reference point. Here's 8,000, and here's 12,000, and then this is about 15,000. Now I'm going to run it up a little higher, and this is about 18,000. How many can hear that? Well, either you have good ears or you're a bunch of liars, but you can probably hear it all right. Actually, up to about age 40, you can hear 15,000 cycles, and after you pass age 40, you begin to lose about 1,000 cycles a year. I mentioned this in a talk a few weeks ago to an IRE section. There was an elderly senior member sitting in the front row, and I noticed he got very pale. And after the meeting was over, I went to him and says, "Hey, what happened there in the middle of my talk? And you got so pale." Well, he says, "I did a little rapid calculation, and I find that in 2 more years, all I'll hear is DC." Well, through electronic means, we can reproduce any one of these frequencies with a high degree of accuracy that we want, and we can get it on call. Now, the next characteristic of musical note is timbre or quality. If you're really highfalutin, you call it timbre. But anyway, this is quality and has to do with the absence or presence of harmonics. And it's this characteristic that gives a note its unique characteristic. I have a little signal generator here. It's a little special transistor oscillator and a toy piano keyboard. And if I sound a note, a simple sine wave, you wouldn't want to listen to too much music with a sine wave tone because it has an empty characteristic. It doesn't sound interesting. But here we have the simplest sort of a note. Now I can throw a switch and I can produce a note that has just twice as many vibrations, and you'll see more waves and you'll hear a higher pitch. Or I can throw another switch and give you just 3 times as many vibrations, and you see more waves and still higher pitch. Now if I take the fundamental and add to it the one that has twice as many vibrations, the second harmonic, you will see a change in wave shape, and you will hear a difference in quality. And that sounds better than, at least it sounds different. And if we take the fundamental and sound the third harmonic, we get another wave shape. Or if I sound the second and third, we get a still different wave shape. We have a sort of a diapason characteristic. Well, if we have then all of these frequencies available, we can take a handful of this frequency and a cupful of that and sprinkle a few others in, and we can put these together in exactly the same way as they appear in a clarinet. And it'll sound like a clarinet because it is made of exactly the same. Well, the next important characteristic of musical note is its loudness. We have a scale of loudness. You start into the threshold of hearing, and we say that's 0 decibels. Hearing is a logarithmic effect, and we use the decibel. And there are a few reference points, like 30 decibel level is a quiet room, and 60 decibels is normal speech, and 90 decibels is an automobile horn at 2 feet, and 120 decibels is a threshold of pain. The power ratio of 120 decibels to 0 decibels is a million times in power. There are some other reference points. For example, 88 decibels is a sound level of a Tuesday afternoon sewing circle, and we know a number of these things. And we can build circuits which will give us any intensity sound that we want, or we can attenuate. You may wonder how much decibels are, and I'll show you. Here's a tone, and we'll just reduce that by 5 decibels. So you have a clear idea now about decibels, and we can proceed to the next point. Another important characteristic of musical note is what I will call the envelope. It's the way in which the sound builds up and dies down. If you think about an organ pipe, you press a key and that opens a valve and wind begins to go and blow a great big whistle. Now the sound of the whistle doesn't reach maximum volume at once. It takes a little while for it to reach maximum volume. And then if you shut the valve off, all of this air is vibrating and it takes a little while for it to die down. So we have a slow rise and a slow decay. If you think about a piano, you have a hammer striking a string. You have rapid rise and slow decay. And if you think about a plucked instrument, you have rapid rise and rapid decay. And so the rise and decay time introduces a characteristic. I have a few rather crude examples of that in a piece of tape here. You can see the first one will be slow rise and slow decay, and you can see the signal rise up. And the next one will be rapid rise, continuation, and rapid cutoff. And the next will be rapid rise and slow decay. Then we have rapid rise and immediate rapid decay. Now each of these notes had the same loudness, they had the same quality, they had the same pitch, but the envelope, the rise and decay times, introduced a unique characteristic to each. Well, again, we know how to make circuits which will give us these rise and decay times and give us any factor that we desire. Sometimes we have to provide means for sliding from one note to another, as in a slide trombone or a violin or the human voice. And this fancy word is called portamento or glide. We, of course, can have frequency shifts from one note to another. And the sixth characteristic is vibrato. We either have frequency modulation or amplitude modulation, and we know how to build circuits to do that. So we have just these six basic characteristics that we have to tie together. However, if you think about a piano, we have 88 notes, and it takes 88 keys to play those 88 notes. Now, if we had to have a key for every one of these characteristics and all the variations, we'd just have so many keys we wouldn't know what to do with them. So we have simplified this coding matter, and we have used a system of coding that to all of you is familiar, I'm sure, namely binary coding. I'll say a little more about that in a moment. I'd like to emphasize that the synthesizer is not a playing instrument. You couldn't come to the laboratories in Princeton and have me demonstrate the synthesizer as you would go to a home of a musician and have him play a concert for you on a piano or any musical instrument. It's a little bit more like you would come to the home of a famous author and ask him to demonstrate how he writes a bestseller. Oh, he'd say, this is quite easy. I have a machine here. This machine has in it all of the letters of the alphabet. And over here's a book. And this book has in it all the words in the English language. And I just take a word out of the book and put it through the machine, and next year will be the manuscript coming out here. So we put our music together piece by piece and bit by bit. And I got sort of interested in this. I thought I'd like to illustrate in broad principles how this worked. And I thought maybe I can use a couple of these elements of musical note and illustrate how you would proceed to synthesize a musical tone. And I found that I could buy from some outfit in the West Coast a chassis like this, which produces all the tones of an octave, a third. Then I got another chassis which provides a number of wave shapes. It does it differently than the one that we have in Princeton, but it does provide a number of wave shapes. And we have a means then of getting the first characteristic of pitch and the second characteristic of quality. Now, in order to activate this, I took apart an old typewriter. I have 4 keys. I only need 4 keys to play my 13 notes. And since you can't see those keys very well, I've rigged it so these numbers will light up. And the first key is number 1, and the second key is number 2. And this isn't a misprint, as most of you know. And if I push the first key down, this note sounds, which is C, and you can see what the shape of the note looks like, and you can hear what that note sounds like. Now the second note in the scale is C sharp. I didn't have room to put all the sharps, so I put a green light back of that one, and we now have C green. And the third note is 2 + 1 or 3, D. And so with just these 4 keys, I already have played 8 notes. And of course, it's almost insulting to say that this is 2 to the 3rd, and that's 2 to the 2nd, 2 to the 1st, and 2 to the 0, or binary system of coding. And in our full-scale synthesizer, we have not 4 keys, but I think we can take a chance in the next slide and just show you what it all looks like without, maybe I'll turn this off just to be sure. And that tells us that we have 2 to the 40th combinations. And 2 to the 40th works out to be about 1 trillion. Now, if we wanted to listen to each one of those for just 1 second, do you know how long it would take? Well, about 140,000 working years. We haven't worked them all out yet. We're at it busily every day. And you see, we have a lot of combinations. Now, while we have this slide on, we might just finish the slides. The next slide shows Dr. Olson and Mr. Ballar. Dr. Olson directed acoustic research. Mr. Ballar did the work. And you see... Dr. Olson is perforating a tape, and Ballar is setting up some of the circuits back. Of each one of these keys, we have an infinite number of combinations, so we really have most anything you want. Now, this is a monophonic instrument. You perforate the tape, and I'll talk about that a little bit later. And after you have this stored on a tape, you can play it back and store it on a record then, 1 row of notes at a time, and after you do this several times, you collect them together, and you have melody and harmony, as I will illustrate in a moment. And just so you don't get an idea, you'd want one of these in your basement, the next slide shows the whole business, 7 relay racks of equipment. Well, now, I'd like to say just a little bit about how we go about synthesizing music. Well, I had these 2 chassis here, and here are the keys, and you can take as long as you want to get the effect. You can push down a note, and when you have exactly the effect they want, you perforate the tape, and it's stored on there, and it's stored for keeps. No more problem with lost chords, you see. So we have this stored up here. And you really you can run this through, take a week to make a tone if you want, or an hour or a minute, and then you make the next one, and then you run it through at regular rate. So you don't ever have to practice playing on this. However, I did get interested in this, and I did a little practicing on it, in company time, of course. And I'm going to brag a little now. I've learned how to play a scale with binary fingering, and I don't think anybody else in the world knows how to play a scale with binary fingering. And so you can see which keys I push down, and you can see the notes go up the scale, and you can listen to the notes coming. Here we go. Whoop, I got a bad note here. Well, we'll get that fixed. So if I want to synthesize a piece, then I will perforate this tape here. And I'll advance it to the next position, and I have other tonal qualities which I can use. And so I have a number of different tone effects, and I can get the effect I want. Well, I'm not going to take the time to do this now, but some days ago when I had a little more time, I synthesized a little piece of music. I'm pretty limited here because I just have 1 octave. I don't have any attack or decay times. I don't have any loudness control, and I only have these few wave shapes that I illustrated. But there is an opportunity for the synthesist to give exactly his own interpretation. This isn't a mechanical device at all. You can get any effect that you want, loud and soft, slow and fast, and you can pursue this. And the nice part is if you make a mistake, nobody need know about it. You just put some Scotch tape over the hole and make a new hole, you see, so you don't bother people with your errors. Well, within the limits of this equipment, I did synthesize a piece, and you might not agree with my interpretation, but that's the way I felt about it that particular day. If I would do it today, it would probably be different. But this is the way I felt about it, and it's stored on this tape, and this tape will now set up those same circuits that I chose on another occasion, and you can see the keys I pressed, and you can see the notes that I played, you can see the shape of the wave that's produced, you can hear what that wave sounds like. So you get a lot for your money right about now. So we'll run this thing through, and if you listen carefully, you might even recognize the tune, but that doesn't really matter. Now I could go ahead and do the alto part, but don't worry, I won't, and we could build this thing up. However, I have some of the early tapes that Mr. Ballar made. I'd like to point out that Mr. Ballar is a fine engineer. He lays no claim to being a musician. In fact, he tells me that he took violin lessons long enough just to convince his parents it wasn't practical. But he is interested in music, and he synthesized a series of tones to produce a melody, and you will recognize this as Blue Skies by Irving Berlin. This is the soprano part, first of all. So that was then stored on one band of a record, and then we worked through the alto part, we put the tape on, and played the tape back, and we then stored the alto part. And then we repeated the same process for the tenor part, and of course if one part we don't like, we throw that away. We haven't spoiled the others. Finally, for a good foundation, of course, we need a bass part. So here comes then the bass part of this simple melody. And now we collect these parts together, and we have melody and harmony. Now, if a dance band were playing this, we'd have to have some rhythm parts. And so we synthesize a series of random low frequencies, wrap them up in the right kind of an envelope, and the result of this looks and sounds like, as you will see in a moment. And for another rhythm effect, we want a little higher pitched frequencies, and so we actually synthesize some noise. And we wrap that up in the right kind of an envelope, and this is synthesized noise. For a more musical rhythm effect, we synthesize a series of very high frequencies, which sound like this, and you can hardly see them because they're such high pitch. Of course, there's nothing like a good deep bass for a foundation. In a synthesizer, you aren't limited. You can go just as low as you like and as loud as you like, and so we have this good deep bass foundation. And now we gather all the rhythm, the bass parts together. Then we may also want to have some notes of rapid rise and slow decay, and so we set up our circuits to accomplish that, and we have the one finger and the piano. And we do a number of those to build up the harmony structure we want, collect them all together, and here we then have piano harmony. May want to have some notes of rapid rise and rapid decay, and so we set up our circuits to do that, and here's an example of such a tone.